In this section, we'll learn how to analyze polynomial functions. But to do so, we need to first remember what polynomials are. Polynomials are expressions containing two or more terms with no negative or fractional powers. Each term may have powers that are either zero or positive integers. Notice that all the polynomial examples on the left have no negative or fractional powers for each of its terms, whereas on the right, there are negative and fractional powers. And if you're wondering why this one is a fractional power, it's because the square root of x is the same as writing x to the 1/2. Whereas what we have here on the bottom, this can be rewritten as 2 times x to the -1. So again, on the right, there are negative and fractional powers. What we also want to notice is that on the left-hand side, again, none of them have negative or fractional powers, but we can also determine something called the degree. Notice that the degree of a polynomial is the largest power of the terms. So here, the largest power is 12. The largest power here is 4, so that's its degree. The largest power here is 23, so the degree is 23. When no power is written, the power is actually 1. So this is a degree 1 polynomial. Here, there are no x's. In fact, we could actually write one in. We could say x to the 0 power, so the degree here is 0. Sometimes it's useful to predict the overall behavior of a graph, and we can do so by noticing the overall patterns of the graphs based on the degree. Functions with an odd degree have symmetry with respect to the origin. So they're going to do something like that, or like this, if it has an odd degree. The leading coefficient when the polynomial is written in standard form, and what we mean by standard form is this is an example of a polynomial written in standard form. This is a polynomial, the same polynomial that is not written in standard form. So in standard form, we want the highest power first, the next highest power next, the smallest power last. So the leading coefficient is going to, when it's written in standard form, is going to determine whether the function will have ends in either quadrants 1 and 3, or if it's going to have ends in quadrants 2 and 4. So whenever the leading coefficient is positive, it actually affects it similar to what would happen with the slope of a line. So here we have a line with a positive slope. And if you notice that its ends are in quadrant 1 and quadrant 3. So if we have a positive leading coefficient, it's going to act in a similar way. So a positive leading coefficient will have ends in quadrant 1 and quadrant 3. Even if something else is going on in the middle, as long as the leading coefficient is positive, it's going to have ends in quadrants 1 and 3. For example, if we were to graph, and you can check this yourself, 3x to the 5th minus 4x squared plus 7, notice it's in standard form. The leading coefficient is positive, so that's going to tell us whatever happens in the middle, the ends are going to be in quadrant 1 and quadrant 3. When the leading coefficient, however, is negative, the effect is similar to that of a line with a negative slope. The ends will be in quadrants 2 and 4. In other words, as x goes to infinity, our function values get smaller, or as x goes to infinity, our f of x goes to negative infinity. Similarly, as x goes to negative infinity, so as our function values get, as our x values get smaller, our function increases. or f of x goes to positive infinity. For example, if we had the function negative 3x to the fifth plus 4x squared plus 7, let's call this g of x. So if g of x is equal to this function, and we were to try to describe the end behavior, we would say that it has an odd power and a negative coefficient for its leading coefficient. So we would expect the ends, whatever happens in the middle, to be in quadrants 2 and 4. In other words, as x goes to negative infinity, we expect our function values to increase. As x goes to positive infinity, we expect our function values to decrease. Roots of functions correspond to x-intercepts. In the case of the graph that we have here, the x-intercept is negative 3. Notice that when we input negative 3 into the function, in other words, substituting it for x, let's see what happens here. We end up with 0. So wherever we have a root, we know that the output will also be 0. Notice that even when the degree of the polynomial is larger, the roots are still x-intercepts. For example, this polynomial, if we were to expand it out, would be x squared plus 6x plus 9, and it would have a degree of 2. As we can see from its factored form, that x equals negative 3 would output a value of 0. In other words, x equals negative 3 would be a root. So on the graph, we see that negative 3 is a root. Notice that x equals negative 3 occurs as a root 5 times in the orange polynomial here, because the power on x plus 3 is 5. Another way of saying this is that the root has a multiplicity of 5. In other words, we know the root here is x equals negative 3, and because of this power of 5, we're going to count that root 5 times. On the green function, the root negative 3 has a multiplicity of 3 because of the power of 3. So this power of 3 makes us count the root here, x equals negative 3, 3 times. On the red function, the root negative 3, or x equals negative 3, has a multiplicity of 1. And why we can say that is if we were to rewrite this, we would put parentheses and a 1 since there's no power. Notice that in all of these cases, the graph passes through the x-intercept. So here it's going to pass through negative 3. Here it's going to pass through negative 3. Here it's going to pass through negative 3. So if a root has an odd multiplicity, the graph must cross the x-axis at that intercept. In each of the following examples, the multiplicities are even, and the graph bounces at the x-intercept as opposed to crossing in the previous examples. So, for example, we know the root here is x equals negative 3 because that's what gives the function an output of 0. So, the multiplicity is 6. Notice that at where the root is, at x equals negative 3, that it bounces. So it comes down, it hits the point, and then it bounces back. For the orange graph, we know again x equals negative 3 is the root because that's what makes this equal 0, and it has a multiplicity of 4, an even number. So again, because the multiplicity is an even number, when we hit that root, it's going to bounce. Similarly, for x plus 3 squared, x equals negative 3 is a root, So at -3, it's going to bounce. The factored form of a polynomial describes all of its roots. In this case, -3 is a root, again because it's going to make the function have a value of 0 when we input -3. This root has a multiplicity of 6. -5 is also a root, and notice that there's no power here. We can write a power of 1, so it has a multiplicity of 1. 2 is a root as well, or rather x equals 2 is a root, and it's going to have a multiplicity of 3. Another important part of our graph is the y-intercept. To find the y-intercept, we just need to set the x value equal to 0 and solve for y. For example, if we substituted 0 for x in the function that we have, this is what it would look like. 0 minus 3 squared times 0 minus 2. 0 minus 3 is going to be -3, so we have -3 squared. 0 minus 2 is -2. -3 squared is +9, and we multiply that by the -2 we already have, and so that tells us that our y-intercept is going to be -18. If we notice on the graph, it's crossing at about -18. The fundamental theorem of algebra basically tells us how many roots to expect from a given polynomial. A polynomial of degree 5 should have 5 roots. So how many roots should we expect from x squared minus 4x plus 9? Because it's degree 2, we expect 2 roots. Remember that roots are x-intercepts. When we graph x squared minus 4x plus 9, notice that there are no x-intercepts because it doesn't cross the graph. So here, this line does not get crossed. So there are no real roots for this function. The roots, therefore, must contain, if they're not real, they must contain imaginary numbers. So the 2 roots we expect from the fundamental theorem of algebra have to be imaginary. What this tells us is that imaginary roots have to come in pairs, and also that they do not appear on the real number plane. So what we mean by they come in pairs is actually they come in conjugate pairs. So as an example, if 3 plus 2i is a root, then 3 minus 2i is also a root. Or if 5 plus 6i is a root, then 5 minus 6i is also a root. This is a conjugate pair, and this is a conjugate pair. So imaginary roots have to occur in conjugate pairs.